Hello and welcome. Let's continue with our lecture on general theory of delivery. In the last lecture, we have seen what is called the parallel transport. Idea here is basically connected with the vector operation associated with two different points. In the case of flat space-time, we have seen that the vector from different points can be added without much problem. Though we have all forgotten what is done in the basic operations of vector is done through what is called parallelly shifting vector from one place to another place. Let's look at this in a little more fully because we have to generalize this to curved space-time. In order to differentiate a vector, we need to subtract a vector from a point B from a neighboring point A and then divide it by the separation and take the limit delta x going to 0. Let's first look at what we do in the case of flat space-time. Let A be a point with coordinate x mu and B with a coordinate with the x mu plus delta x, where delta x can be very small. Eventually we want to take the limit delta x going to 0. We have a vector field here, that means each point will have a vector connected with that. Let T alpha be the vector field which we are looking at it and whose component is given at point A is T of alpha A and whose component at point B is given T of alpha B. Now what we do is that we drag the vector from point A to B along a straight line, and we also maintain the angle same, that is we drag in a parallel fashion. That means we form a parallelogram and move the vector along that as shown here. So we have a point connecting A and B, then we draw a parallel line and then we drag the vector along this and take it to the point B and then subtract between them, and that subtraction be done because all the vectors are at same point. We can call that subtraction as a delta alpha and then divide by delta mu and then the take limit delta mu going to 0. That gives us a differentiation. There are obvious difficulties doing this in a curved space-time. We can have a same set of geometry. We can have a point A with coordinate x mu and we can have a point B with coordinate x mu plus delta x. We have a vector field at T alpha A at A and then T alpha B at B. These two are the component of the vector at that point. So we have to take the vector from A to B to do any operation at point B or B to A. It can be done in one of these points. Only you cannot mix up the point. So it is not possible to have a straight line. In the curvilinear geometry, it may not be possible to connect 2 points by straight line. Of course, you can make them bring very close to each other and connect them. That is called curvilinear geometry. But however, given our physically separated 2 points, it may not be possible to connect it by a straight line. So in such case, we got to take them to the arbitrary path. That is what is called the parallel transport. Now the parallel transport is you transport it along any curve A to B and then retain the orientation of your T alpha with respect to the tangent of the curve. Now you see that this transport acquire a additional component or small change because you have taken it along a wiggly curve, and that is what we call is a delta. Now we have seen that for a sufficiently small curve, we can assume it to be linear to the separation between the point, and we can also take it to be linear with respect to the vector itself. So this leads to the connection coefficient, which takes all the linear combination of these. This connection coefficient itself may depend on the position of the vector, and this is how you take a vector from one place to another place and then you can do all the operation. Now in this lecture, we are going to look at how to define the derivative by taking the parallel transport and then do it consistently so that the derivative itself become a tensor. We have earlier seen that the partial differential is not a tensor. Now we demand that so-called derivative should transport like a tensor. Then we obtain the condition on gammas, or they are called connection coefficient. So that is what we are going to do in this lecture. So it's a prolonged recollection because now lectures are going to go very quickly, and if you don't pay attention, is going to remain a hazy path. This would form a basis of all our coming lectures and differential geometry. The differentiation is very important part, and I am repeating several times. This may get to boredom. However, it is important to note that this concept need to be followed more carefully. Let's continue with the lecture. Okay, we start with the deriving a derivative operator which would act as a tensor while transforming from one coordinate system to another coordinate system. Such derivatives are covariant derivatives. The covariant comes because it can be transformed from one coordinate system to another coordinate system. We have called such objects are covariant. In addition to that, they are also increasing a rank of tensor by one covariant rank that we will see little late. We follow the standard operation for differentiation. We take a vector field at two different points. Now we know how to take vector from one place to another place using parallel transport. We do that and then subtract them and then go through the standard definition of differentiation. Let T alpha be vector field defined throughout the space-time. Let P is equal to x alpha and Q is equal to x alpha plus delta x alpha be two infinitesimally close neighboring points. We have a vector field which is defined at these 2 points, that is T alpha of P and T alpha of Q, and then we do parallel transport. We have seen that when we do a parallel transport, a small change comes into the vector. That small change in vector T is called the delta T with the index rho. Now T alpha is parallelly transported from point P to Q. So let's pictorially see it. We have a point P and we have a point Q, and then we have vector field at P and we have vector field at Q. We take a curve and parallelly transport. That transported vector will acquire an additional component delta T beta, and that we subtract from T of beta at Q. So equation is written as covariant derivative, that is called the delta alpha T beta, as given as a limit delta x alpha going to 0, 1 by delta x alpha into T beta of x alpha plus delta x alpha. This is a component. This is a vector field evaluated the point Q, and then we have T beta plus delta T beta which is transported from T. Now we have a vector at Q. We have a vector parallelly transported from P to Q. So now we subtract them. Now we have seen earlier delta T beta can be written as gamma rho beta alpha and T rho delta alpha beta. We have assumed the change acquired because of parallel transport takes this form. So that is the expression for the delta beta. Now we can also get the T beta from the Taylor expansion at point P, that is T beta of x alpha plus delta x alpha can be written as T beta at x alpha, that is at P, plus T beta dt beta by dx alpha into delta x alpha. Now the Taylor expansion always can be done for a smooth vector field, but important point to note is that this Taylor expansion is not a tensorial, as we see that we have partial differentiation here. Partial differentiation do not transform like tensor, so this leaves expression is not a covariant. We have these two terms for the derivative. One we can obtain from the Taylor expansion, the other we can obtain from the parallel transport, and by substituting this we get first one using a Taylor expansion, we get the partial differentiation, and then second one is parallel transported. We can see that these two terms cancels out and leaving out the result limit delta x beta going to 0 into 1 by delta x beta into partial differentiation of T alpha with respect to x beta into delta x beta minus gamma rho alpha beta T rho delta x beta. It turns out that we can easily factor out the x delta x beta, and then we are dividing it, that term cancels out. This leads to the non-vanishing term as limit delta x beta going to 0. So this is what we get eventually for the covariant derivative, that is the delta alpha T beta is given as a partial differentiation of T alpha with respect to x beta minus gamma rho alpha beta T rho. So as I already told that this differentiation is called the covariant differentiation. Only input which goes in is a gamma. How you relate the vector field from two different places, that parallel transport rule one need to define. There is no straightforward way or unique way to define. you always have to define connection. You always can define a covariant differentiation. Let us look at more about this connection. We have defined the covariant derivative with respect to connection gamma. So interesting fact here to notice is that we have a partial differentiation which is not a tensor, which we have already shown, and we also have a connection which might not be a tensor, and then what we have is a covariant derivative. Now we can impose the condition on connection on gamma such that the derivative operator which we have defined need to be tensor. So this is a strong constraint imposed on your covariant differentiation in terms in the connection coefficient or gamma, such that our covariant derivative remains tensor, and what would be the constraint on the gamma. So it is an easier exercise to do, bit involved, because you can see that already we are getting into tensor analysis. Our derivation becomes longer and longer, which involves more indices. I often prefer to use Latin indices for the 4-dimension and Greek indices for 3-dimensional, because now onwards we rarely use only 4-dimensional, and I at least know 26 Latin alphabets, while freely writing I seems to hardly remember any Greek indices other than alpha, beta, mu, nu, and delta, gamma. However, this time I seems to have changed my notation, and this might lead to confusion here and there because I am not very fluent in Greek. Here we derive a transformation rule for gamma or connection coefficient such that the derivative operator delta alpha operating on a covariant vector transform like a second rank covariant tensor. So this is a way of constraining gamma and bringing it from more general case to restricting it so that we can use them in standard geometry and apply them to expressing the laws of physics. Let's start with the covariant derivative of a covariant tensor in an x prime system, and then we transform it to x coordinate system and put the condition that the covariant derivative transform like a second rank tensor. So let's expand expression for covariant tensor in terms of gamma. Note that partial differentiation with respect to x prime variable, so is the gamma is in the x prime system and the tensor itself is in the x prime. So this is the expression for the covariant derivative of a covariant tensor which we have determined earlier. Also use the transformation rule for the covariant tensor. We have a covariant tensor. We have covariant tensor here and we have a covariant tensor here. Let's transform that to x coordinate system, and the transformation rule is given here. Substitute in this expression and we would get expression like this. First is a partial derivative coming from here, and the second is the expression for the tensor after the transformation, and the same way here is the transformation law and then the gamma symbol. So now we can expand this first term and we would get the two terms because of the product rule. So the first term is a derivative of the tensor in the x prime coordinate system, and then we have a derivative of the coordinate transformation or the derivative of transformation matrix, and then we have the final term which is not changed in this. Let us also look at this. Before going any further, let's rewrite this equation collecting all the relevant terms. The first term is essentially coming because of the transformation. We are rewriting differentiation with respect to x variable, you can say it like that, and the second and third are having the common factor of a t sigma. Now if this quantity, that is a covariant derivative, has to transform like a second rank tensor, we can expect it to be a second rank covariant tensor. We can write a direct rule for the transformation of second rank tensor. That is basically two indices have a two multiplicative factor of transformation. Now here again we use the definition of a covariant derivative in the new coordinate system that can be expressed in terms of gamma, and that is given here. So we replace this covariant derivative explicitly in terms of the partial differential and gamma. This expression we can directly compare with the expression given here which we obtained earlier for the covariant derivative in the x prime system and related to x system. If it were a tensor, then it is this rule which it need to be followed, and those two have to be equal, and immediately we can simplify. Some of the terms get cancels out. We can see that this term term and this term is same, so it cancels out, and then we are left with the 3 additional term which put the condition on the various quantity involved. Cancel the common terms and we rearrange the remaining term, so we can basically get this last term here and the second derivative term, which are basically problem causing term because they are not transforming according to the tensor rule. Finally, which are the term involving the gamma. Since the tensor T sigma is arbitrary here, we can simply get rid of them. This expression should be true for an arbitrary tensor. It should not be a specific to the tensor which we are differentiating, or T sigma, the tensor or covariant vector. We can get rid of the tensor T sigma and then resulting in an expression which would basically relate gamma prime and the gamma, that is gamma in the 2 coordinate systems. So this is exactly is what we are looking. If the gamma satisfies this transformation rule, then we know that the covariant derivative of a covariant vector would transform like a second rank covariant tensor. Now we can multiply this by dx prime nu by dx sigma. So it is basically rearranged a term. The basic idea is to get rid of this term. So when we multiply, it simply reduces to the delta nu rho, and then that can be absorbed in this expression, which is giving us the direct expression for the gamma prime in terms of gamma. So let's multiply these 2 terms, simply leads to the delta function, and then we have these 3 terms. This would look very similar to the tensor transformation of a third rank tensor, which has a 2 covariant rank and 1 contravariant rank, and this is a troublesome term which is not essentially a tensor. So we eventually found out we can easily simplify this, and then we get the transformation rule for the gamma from one coordinate system to another coordinate system. As I have already mentioned, this looks like a third rank tensor transformation. This one which does not have any explanation, because this is exactly similar term which caused the trouble in the partial differentiation and made it a non-tensor. And so here also we have a similar term. That means that gammas do not transform like a tensor. So this shows that if gamma satisfies this transformation rule, your derivative, the covariant derivative, behaves like a tensor. So this has fulfilled one of the major criteria which we needed, that is we want a differential operator. However, there is an arbitrariness here. We seems to have a very vague condition on gamma such that derivative operator becomes a tensor. It is general enough, that is why you can put any arbitrary gamma on a given coordinate system, since it follows this transformation rule, and we can compute gamma in any other coordinate system. So this way you can find it out in an arbitrary coordinate system. It need to follow this transformation rule. It is in general not a tensor quantity. So this is explicitly saying that we have got the expression for the transformation of gamma from one coordinate system to another coordinate system such that the derivative operator becomes a tensor. So we see that the gamma is not tensor because of this term. So that is not very surprising. We have seen that when we express the derivative operator, we have had 2 terms there. The first one is a partial differentiation and the second one is a gamma term. The first term is not a tensor, so this we have seen earlier, and now currently we see that the second term is also not a tensor. Somehow the subtraction of 2 non-tensor quantities cancels out the term which we are not interested in and results in a quantity which is purely tensor. It is like a magic where you cleanly get rid of the terms which you are not interested, give a pure tensor quantity. It is still clear that we don't know what is gamma. Gammas are just relay tensor from one place to another place. That is why it is called connection, and this you can use to find the differentiation. Now gamma is not unique. There don't seems to be any concrete constraint on gamma other than there is a general transformation rule which it need to satisfy. So this leads to interesting consequences. Not having a tensor, sometimes it is good to have tensors because it follows a very definite transformation rule. Sometimes we have an object which are not tensor, they are good too. Now for example, this gamma is not a tensor. What is the advantage? Advantage is that you can choose gamma whatever you want in a given coordinate system. Say for example, you may ask whether you can choose gamma to be 0. Yes, you can choose gamma to be 0, and then your ordinary differentiation becomes the covariant differentiation. But we seems to have said earlier that the ordinary differentiation becomes the covariant differentiation only in the inertial coordinate system. That is true too. The idea here is that the property that gamma is not tensor makes it somehow magical. Earlier we have seen one of the rule in the tensor transformation is that if a tensor is 0 in one coordinate system, it remains 0 in all coordinate system. However, you see that the gamma is not a tensor. It has a very funny transformation rule, but it don't have to follow this rule. Gamma can be 0 in one coordinate system and gamma need not be 0 in other coordinate system. This is a very powerful idea that you can choose your gamma to be 0 in a given coordinate system. So we have been doing it knowingly or unknowingly. For example, all our Lagrangian, we started with the Minkowski space or flat space time where we had a kinetic energy simply square of velocity and all the metric components were constant. We have done a non-inertial transformation from the Cartesian coordinate system and gone to spherical polar or any other coordinate system in which your gamma is not 0. So we have started with the coordinate system in which all gammas are 0 and ended up in another coordinate system where gamma is non-zero. We know the transformation rule from the Cartesian coordinate system to polar coordinate system, and gammas are non-zero in the polar coordinate system. We have seen that in the Lagrange equation of motion, resulting in a complicated equation of motion. This interesting properties of gamma is resulting because it is not being a tensor, you have a certain amount of freedom. But once you choose gamma to be 0 in one coordinate system, your freedom usually goes. The coordinate transformation rule given here in this equation need to be applied, and that equation will determine what are the component of gammas in the other coordinate system. But at least you can choose one coordinate system in which the gamma is 0. Later we will see that these are called the locally inertial coordinate system. Let us go ahead and look at what happens to the covariant derivative of contravariant vector. So we have earlier seen that the covariant derivative of a covariant vector is a second rank covariant tensor. So with this analogy, it should be clear that the covariant derivative of a contravariant vector should be a mixed tensor with one covariant and one contravariant tensor. So how do we get that? We can use the same algebra which we have done. We know what is the definition of covariant derivative of covariant tensor. We know how the gammas transform, and we can use the same thing and then get the expression for the covariant derivative of contravariant vector. There is another simple way. Another important point to notice is covariant derivative of scalar is also its ordinary derivative or partial differential. So that is simple to see that the gamma is coupling because of T rho transform. T rho is equal to f, and which is a scalar, which is a simple transformation and do not play role. So that the gamma is not necessary in this case, and simply you have a partial differentiation. Which from completely independent point of view, we have also defined covariant vector themselves as a gradient of a function. From that point of view, we can also show that the gradient of a function transforms like a covariant tensor. So this way, it is clear that the covariant derivative of function is simply a partial differential. We can use this fact to find out the covariant differentiation of a contravariant vector. So how it is to be done? You simply construct a scalar. You can construct a dot product with the covariant and contravariant vector. So now it is a scalar. So this scalar should have a covariant derivative as ordinary derivative. Now this can be written as dot product between the two vectors T alpha and T beta, or you can also write them as a one covariant and one contravariant, because you can use G alpha beta to raise the index of T from covariant to contravariant. And this is what you result. Now you simply apply the differentiation. Differentiation, when you are applying, basically using the product rule, that is should be true for all the differentiation. And when you do the differentiation, you end up with the two terms. The first one is differentiation of contravariant vector T, and then is a differentiation of covariant vector U. So these are the two terms. Now we can explicitly express covariant differentiation of a covariant vector, which we already know from this equation.
It has become a little messy. Let's clean it out.
So we already know how the covariant differentiation of a covariant vector. Substitute it here from this equation and then you have this expression. Now let's play another game. F is defined as a dot product. Let's take a partial differential. This is a tensor now. But however, let's look at these two terms. This is again a partial differentiation, which is also a differentiation but may not be transforming as a differentiation to another coordinate system. You can simply use the product rule and write the ordinary differentiation of a contravariant vector and a covariant. Individual terms here may not transform like a tensor. For example, we know this is not a tensor, this is not a tensor, but the whole sum would somehow behave like a tensor because this is a tensor. So now we can compare these two equations here and then cook this up to get the expression for the covariant derivative of a contravariant vector. Okay, this is what we have. This is what we have obtained. This is what we got comparing these two equations, and we can get rid of the, as u is completely arbitrary vector, it should not depend on the u. Both t and u are arbitrary vectors, so we can get rid of anyone which we want, but u factors out cleanly and we end up getting an expression for the covariant derivative of contravariant vector. Now it comes with the plus here it comes with the negative, so these two cancels out and make the gradient as a pure tensor. So again, this is a magical property, is what we see covariant derivative of both covariant and contravariant vector. So still we do not know what is expression for gammas. So gammas need to be determined. Now the gammas are arbitrary, there is no constraint on them, we know how they transform. This makes the whole covariant differentiation a completely arbitrary. Define your own gammas and come up with the differential operator. And that's a valid differential operator because it satisfies all the necessary conditions. So we need to find out gamma, which is closely linked with the geometry, and that is what we are going to do next and get some example to visualize. So I want you to do a homework, essentially derive these two. So derive the transformation rule for gamma as given here, basically reproduce whatever I have written. It is good to write with your own hand and submit it, and that's going to be the assignment which need to be submitted in a week's time. We'll stop here and we'll continue in the next class